Elementary statistics practice test number 2, module 2, covering chapters 4 and 5. Here's chapter 5, discrete probability distribution. Does the table describe probability distribution? What is the random variable? What are its possible values? And are its values numerical? Number of gears in 3 birds. X represents the number of gears 0, 1, 2, 3. And P of X is the probability of each case. So therefore, this is known as probability distribution table or discrete probability distribution table. Number 1, the variable X, which is the number of gears in 3 birds, 0, 1, 2, 3, it's a numerical random variable, and its values describe probabilities. Number 2, add them up. They must add up to 1. And again, this is what you want to pay attention to. If they don't add up to 1, this is not a probability distribution. However, if this number is very close to 1, such as 1.00000, many zeros and then 1, or 0.99999, that's okay, because it could happen due to round up error. So if you add them up, it's either 1 or extremely close to 1. This part is fine. And the other one is that each value must be between 0 and 1. Can it be negative? No. Can it be more than 1? No.
In a game, you pay 60 cents to select a 4-digit number. If you win by selecting the correct 4-digit number, you collect $3,000. How many different selections are possible?
Great. So we have 4 digits. Remember, we have 10 digits from 0 to 9. Therefore, there are 4 spots. 10 times 10, 4 times. That means 10 to the power of 4. So 4-digit number. We have 4 spots, 10 to the power of 4. What is the probability of winning? Probability has a specific definition, n of winning over n of s, which is 1 over 10,000. If you win, what is your net profit? Remember, you already paid 60 cents, so it comes out of that. So $3,000 minus 60 cents is the net profit. We want to come up with the probability distribution for this net profit. So numbers, if we win $3,000, one winner will win $3,000. The rest will not. We have total of how many tickets or how many players? 10,000. Net gain for the winner is this much. For everybody else is negative 0.6. So this much for the winner, this much for the rest. What is the probability for winning is 1 out of 10,000, and for losing is the rest of it, 1 minus that. So this becomes 0.0001, this becomes 0.9999. This is part D. Find the expected value, do the interpretation. We're going to come up with the following. The product of x p of x and add them up becomes mu. So let's multiply these two, let's multiply these two, and let's add them up. Then this one says x squared. Square this times this one, square this times this one. So take a look at what happens. I want to make sure we understand. We are multiplying these two, we get this number. We are multiplying these two, we are getting this number. We add up and we get negative 0.3. How do we get this one? Square this number. X squared times this number. Then square this number. Minus 0.6 squared becomes positive times this number. Add these two, and you come up with that. Why are we doing that? Mu or summation of x p of x is negative 0.3. Sigma squared has this formula, and sigma is the square root of that. Sigma is the square root of that. You can use either this formula or this formula, it doesn't matter. So that's why we have this minus mu squared. When we do the math, we end up with this. So find the expected value. The part that is asking for find the expected value, this is it, and you're done. But what does it mean? The interpretation is that everybody gains this much. That means everybody, because it's negative, everybody loses this much. 30 cents on average, including the winners. So on average, all players, a player loses, or all players, how much? $0.3 or 30 cents per ticket with a standard deviation that we just calculated, 94.85.
A pharmaceutical company receives large shipments of aspirin tablets. The acceptance sampling plan is to randomly select and test 24 tablets. The entire shipment is accepted if at most 2 tablets do not meet the required specifications. If a particular shipment of thousands of aspirin tablets actually has a 5% rate of defects, what is the probability that this whole shipment will be accepted?
Excellent. And that's important to see what we are dealing with. Remember, in statistics, we are dealing with word problems. So what is given? You're dealing with a binomial distribution. Why is that? Either works, either it's good or not. Either it's defective or not. 2 outcomes. How many? We're going to choose n equals 24. What is the probability of defect? 0.05 or 5%. So this is a binomial distribution. And this is a quality control because they can't check each and every one of them. They do check a sample randomly. And the randomness is the key. So probability that is binomial distribution has the following definition. Binomial experiment and probability distribution properties. We have n identical trials. Each repetition of the experiment is a trial. Each has only 2 categories, like true, false, tails, heads, defective, not defective. Probability stays constant, and they are independent trials. This P is called the probability of success. It doesn't mean anything positive. It's just a wording that is used by statisticians. Therefore, we are using this formula. We are going to replace the n with 24. We're going to replace the P with 0.05. We also know Q is 1 minus P. So we calculate the value of Q, and we plug everything into this formula. Notice everything is ready to go. What's missing is X. All you have to do, replace the X according to the question. So going back to the question, the entire shipment is accepted if at most 2 tablets, at most 2 tablets do not meet the required specs. So probability of X less than or equal to 2. That means you calculate the probability of X equals 0. X equals 1, X equals 2, add them up, and that's the answer. So in this formula, you got to replace the X with 0, do the math. 1, do the math. 2, do the math. Add them up. So we want the probability of X equals 0, X equals 1, X equals 2. And at this point, as long as you're showing all of your steps here, you can use a calculator to come up with that. Or you can do it by hand. Either way, you're ready to do it by hand. Just plug in. If you were to do it by a calculator, here's the TI command. Second variable is binomial PDF. And so if we put this, PDF gives you one value, CDF gives you all of it. And it depends how many decimals you want to use. 88.4%.
It is known that 70% of managers of all companies suffer from job-related stress. What is the probability that in a sample of 20 managers, exactly 8 suffer from job-related stress.
Excellent. Again, it is a word problem. So what is given? It is a binomial distribution. Why is that? We either suffer from stress or we don't. So there are two outcomes. N, Tony, P, 70% or 0.7, exactly 8. We are going to stick with the formula. When P is 0.7, Q is 1 minus that, or 0.3. Let's put it into the formula. Into this formula, we replace the N, P, and Q, and we keep the X just the way it is, because this is the general formula for this question. Now, for part A, we are going to replace the X with 8. Again, put it into a calculator or do it by hand. If you use a calculator, it gives you this number, and you can put it here. Now, again, how many decimals? I stopped here. 2 changes to 3 because the next number is 8. So when you do the rounding, be very careful. At most, 8 suffer from job-related stress. That means the probability of X less than or equal to 8. That means in this formula, we plug in 0, 1, all the way to 8, and we add them up. Clearly, we don't want to do that by hand. And you can use a technology, but you're showing your work step by step. So it means this. Now technology will do the job for us. Binomial CDF, N is Tony, P is 0.7, X is 8. We end up with the answer, and we write the answer with a bunch of decimals. Again, look at this number is 8. The next one is 1. This 1 depends on this number. Remains or changes. Because it's 6, it changes to 2. It is known that 70% of managers of our company suffer from job-related stress. Same question. So what about at least 9 suffer from job-related stress? Let's see how it works. We are looking at the same question. We are just looking at the different part. Probability of X larger than or equal to 9 means probability of X equals 9, 10, all the way to N. N happen to be 20. So probability of 9 all the way to probability of 2. And we also know that it's 1 minus probability of X less than or equal to 8. And the good thing about this, we've already calculated this from the previous part. So 1 minus the previous part is the answer. Expected value, mu equals NP. Plug in. Standard deviation, sigma is square root of NPQ. So sigma squared is NPQ. Take a root, and however many decimals that they ask us. Would it be unusual to claim that 7 managers from this sample suffer from job-related stress? Mu plus minus 2 sigma. That was the range rule of thumb. Mu is 14. You're going to multiply this number by 2, subtract from it, also add to it. So mu plus minus 2 sigma. That means 14 minus 2 times 2.05, 14 plus 2 times 2.05. So the numbers go from 9.9 to 18.1. Anywhere from here to here is usual. Less than 9.9 is not, it's unusual. Larger than 18.1 is unusual. Because number 7 is not in this range, it's unusual. This is in set theory, and it's red. This would be an element of without the line through it. This is not an element of. This is the notation in set theory, not an element of. Therefore, it is unusual. I want to find the probability of a couple having at least one girl among 3 children. There are different ways of approaching it. I like to approach different methodologies so you'll be comfortable with that. One is probability of at least one is 1 minus probability of none. And probability of none, remember, we are assuming the probability of G and probability of B is identical is equal to 1/2. None means all of them are boys. That means 1/2 to the power of 3. So 1 minus 1/2 cubed is 7/8. What is this? This is the probability of none. None means no girls, all boys. The probability of each one is 1/2. So 1/2 to the third. We are assuming independency. There are more to it than that. So sometimes the knowledge of biology, it helps, but we are assuming independence. Here's the second method. We can use binomial distribution. N is 3. There are two outcomes, B or G. P is 0.5. So we want X larger than or equal to 1 because we want at least 1. That means 1 is good, 2 is good, 3 is good. So we calculate each one and we add them up. So this is the formula we need to use where N is replaced with number 3 and P is 0.5. Q happen to be the same, 0.5. So this is the general formula. We don't write the X yet. We have N, we have P, we have Q. Now for number 1, we replace the X with 1. For number 2, the same thing with 2. For number 3 with 3, we calculate each case, we add them up. Now, again, it's easier to go with 1 minus probability of 0 because we have all the way from 0 to 3. So let's calculate just 0. So in this one, calculate the probability of 0 and subtract it from 1. It gives you the same answer using binomial distribution, and it is a tad faster. An alarm clock has a 0.9 probability of working. What is the probability that it will not work? It's a complementary event. Probability of working, let's say W represents working, is 0.9. So not working would be 1 minus that, which is 0.1 or 10%. What is the probability that two such alarm clocks will not work? This is the concept known as quality control that companies do use to be on the safe side. Probability that the first one works, probability of W, let's say sub 1, and the one with the not bar at top of it, the probability that it won't work. What is the probability that two such alarm clocks will not work? What is the probability that both of them fail in this manner? Probability of the first and the second alarm not working. We are considering them to be independent. Each one has a probability of 10%. When you multiply it, it becomes a lot less. It becomes 1%. There is 1% probability that both fail. And that's the concept known as quality control. It's extremely important. Generally speaking, they are independent. The only way they can become dependent if they are both plugged in and there is no juice. Therefore, they both shut off. That could happen, but normally they are considered independent. So if the power goes out for any reason, then they become dependent in essence. What is the probability of being awakened if you have two such alarm clocks? The assumption is we wake up if any of them works. Well, there are different ways of doing it. One, probability of being awakened is 1 minus probability of not being awakened. That means the two fail to work. That's really the meaning of it. We are assuming waking up into the alarm. And so 1 minus 0.01 is 0.9. That's the easiest method and you're done. But we could have a different take on that. For example, for method 2, if we use addition method, probability of A union B is probability of A plus probability of B minus probability of A intersection B, where A and B, both of them are working, W1 as well as W2. So the first one working, union W2. Using this formula, the first one working, there's a 90% chance that works. Remember, 10% failure, 90% for this one, 90% for this one. Minus, now this two, we multiply P of W1, which is 0.9, times P of W2, which is again 0.9. So this part is P of W1 times P of W2, which is 0.9, Gives you the same answer, 0.9. The third method using binomial distribution. N is 2, because we have two alarm clocks. Probability of working is 0.9. So this is the general formula. And we can calculate the probability of X by replacing N with 2, P with 0.9, Q with 1 minus that, which is 0.1. And we want the probability of X larger than or equal to 1. That's important to see why we want that. Probability of X larger than or equal to 1, as long as one of them works is fine. So probability of X equals 1 has to be calculated, so replace it with 1. 2 has to be calculated, added up, or 1 minus probability of 0. So calculate this with 0, subtract it from 1, and that gives you exactly the same answer. So there are three different approaches, all of which give us the same answer.
During an NFL season, there were 256 games played with 1,307 touchdowns scored. Poisson distribution. What was the mean number of touchdowns scored in each game during the season? Round the answer to the nearest.
0.0001, 1/10,000. Poisson distribution has a specific definition, the probability of the event occurring X times over some interval. The interval could be interval of time, distance, area, volume, you name it. And it's given by P of X equals mu to the power of X times e to the power of negative mu over X factorial. E is the base of natural log. You may remember it from intermediate algebra, 2.71828, and it continues indefinitely. Mu is the mean number of occurrences of the event in the intervals, and the parameters are mu and sigma, where sigma is square root of mu. So what is the mean? The mean is the number of touchdowns. And so we are going to divide that by the number of games. The mean is the number of touchdowns divided by the number of games. So we have this many touchdowns, we have this many games. The ratio, and we use many decimals, in this case 4. So we write with more decimals to make a decision. This is the one, number 4. Next to it is 6, and therefore we change the 4 to 5. So pay attention to the rounding accordingly. So the formula for this Poisson distribution, which is mu to the power of X, now we change the mu to this number, e to the power of minus mu, minus 5.1055 over X factorial. So that's the general formula.
On January 10th, 2010, the Green Bay Packers and Arizona Cardinals played a playoff game in which there were 13 touchdowns scored. What is the probability that a random game would have that many or more touchdowns?
Excellent. So using Poisson distribution, probability of X larger than or equal to 13 means 1 minus probability of X less than or equal to 12. If we were to do it by hand, it means replace the X with 0, calculate it. 1, 2, 3, all the way to number 12, calculated. Add them up, subtract it from 1. It's a lot faster than going from 13 all the way to N, which is 256. If we were to do it by hand, needless to say, we don't have to do it by hand. We show our work here, and now we use the technology. Here's the TI command. Second variable is Poisson's PDF or CDF. In this case, lambda is given here. The X value is 12. We paste it, and then we subtract that from 1. I hope you realize what happens. This is when you go all the way to 12, becomes this number. This has to be subtracted from 1. So I multiplied by negative 1 plus 1, and we write the answer with a bunch of decimals. They want only 4. Now for this column, notice the first column lists the number of touchdowns. Now this is the probability. And the third one is the prediction, how many games is your best prediction about the number of games during the season that had that many touchdown scores. I'm going to just show you a couple of them quickly, and the concept, needless to say, not going to go through the whole thing, but remember this was the formula when we worked on it. So let's plug in 0 for this one. We want to calculate this entry. Plug in 0. Anything to the power of 0 is 1. 0 factorial is 1. So the answer is only this one. The answer is this one. Using a calculator, or just go with the Poisson PDF, putting 0, and that gives you the same answer. So this is the same answer that goes in here. This is the same answer. Now, how about the predicted number of games? We are going to multiply the probability here by 256. So when I do that, I get this one. And I'm going to write it here, but I'm going to write it here as a whole number. So this one is 0.006063, whatever, however, I want 4 of them. So I'm going to write simply 0.0061. This one is 1.55, and I'm going to put it as 2. So the first one is this one. Again, you really don't want to write it like that. I'm just showing you with 4 decimals, this number 0 class changes to 1 over here times 256, and you round it because the number of games, it's a whole number. What about the second one? Now you're going to go back to this formula and replace this with this x with number 1, comes up with the answer here, and then multiplied by 256. You're going to continue for all of them. As an example, if you go with the next one and multiplied by 256, you see these two numbers, it's been basically plugged into a calculator. And the next one plugged into a calculator. So take a look. This number, 0.3096, you're going to multiply this by 256, you get 7.924. So we're going to round it to 8. Notice it's rounded to 8. Then for the next number, when x is 2 here, if you do the math, you end up with 0.0790, continue indefinitely, 025, let's say. I'm putting more decimals, class. You want to stick with only 4, but I'm showing you more. You multiply by 256, you get 20.23. When you round this to the nearest whole number, it becomes number 20. So this is how it works, and you can continue finishing this off. The concept is straightforward, and that's the key here.